Whenever we make a measurement, we can never measure anything 100% precisely because there are always going to be limitations caused by the measuring instrument that we use. So we could say that all measured values have some uncertainty. Now, another term that sometimes is used for the word uncertainty is the word error. Now, you tend to think of error as meaning you've made a mistake. In this context, the word error simply means that something cannot be exact. There's a certain amount of uncertainness, hence uncertainty in the readings that we get. All right, so how do we go about estimating uncertainties? In general, the uncertainty in a reading is going to be equal to the smallest scale division. I think in the previous little video we talked about using a meter rule, which measures to the nearest millimeter. So the uncertainty would be what we say plus or minus 1 millimeter. That would be the uncertainty. We could be within 1 millimeter of what we expect it to be. And the maximum amount of uncertainty that we use, which is what this figure here is an indication of the sensitivity of the scale, or another word we use is the term precision of the instrument being used. If we go through these three devices here then, a rule which measures to the nearest millimeter would have an uncertainty of plus or minus, or a maximum effectively, uncertainty of plus or minus 1 millimeter. Vernier calipers that measure to the nearest tenth of a millimeter, plus or minus 0.1 of a millimeter, and the micrometer screw gauge, plus or minus 0.01 millimeters. So it's a reflection of the precision of the instrument that is being used. Right, here's an example. We will at some point during the year do a practical like this as a practice AS question. A student measures the height to which a table tennis ball bounces by observing the bounce with a meter rule behind the ball. She does this 6 times, getting the following heights. Now the ball bounce is going to be a little bit variable, and it's pretty difficult to judge. So we don't get exactly the same reading each time. So what we have to try to do is figure out the best estimate for the height and what uncertainty there would be in that. So what I'm going to show you here is the technique that you should use. I want you to copy out this example and to work through it in your own notes. All right, so if you take the average of all those figures on the previous slide, the average is 48.917, but that's at present being quoted to 3 decimal places to the nearest thousandths of a centimeter, not reasonable. So how do we go about figuring out the uncertainty? What we need to do is to find the range of the values. So you need to find the largest value in here. What's the largest value going to be? 50.4 is the largest value, and then find the smallest value. It looks to be 47.3. Okay, I'll leave you to figure out the difference between those two values. The difference is going to be the range. And then to figure out the uncertainty, it will be plus or minus 1/2 of the range. So take the range of values, that's the biggest minus the smallest up here, biggest minus smallest. Take half of that, and that is going to then give you the uncertainty. Having got the uncertainty, you can then work out the say plus or minus whatever that uncertainty is, and you round the actual length value off to match that. So we'll discuss this one a little bit in class as well, just to give you a few more ideas about that. Precision and accuracy, 2 words that in everyday language we might think means the same thing, but they have quite distinct meanings. Precision, let's see what it says here. The number of significant figures quoted indicates the precision. All right, so the number of significant figures quoted indicates the precision of, let's make it in black, shall we? Is that any better? Of an instrument. All right. So it is possible that readings could be precise due to the type of instrument used, for example, micrometer screw gauge, but not be very accurate. The term accuracy here is concerned with how close a reading is, or a measurement is, to the true value. So it is possible, for example, with a micrometer screw gauge, to get a reading to the nearest 0.01 of a millimeter, so it will be precise. But let's say that micrometer screw gauge has got a zero error in it. If there was a zero error, it would mean to say that all of the readings would be out by a certain amount, and therefore we might not necessarily be accurate. So I want you just to note down the points that are on this page here, please. And we've talked about this already. Effectively, then a micrometer screw gauge with a zero error, it will be precise, but not accurate. Oops. Okay, so here's an indication of the sorts of things that could happen. Let's say we got everybody in the class to use a particular instrument to take a measurement, and we record all of those results. We'd expect possibly some type of normal distribution, a little bit like that. If we plot everybody's results, you'll get some people getting something, significantly smaller than the real thing. Some people getting something significantly bigger, but we'll probably get most of the results clustered around the true value. Now, the true value is something you can't measure, but that's what's represented by this T here. All right, so in this situation, because the results are centered on the true value, then is the thing going to be accurate? The answer would be yes, it will be accurate. But if you have a look at the spread, and this is a relative term here, the spread of this graph, it's a pretty wide spread compared to maybe something a lot more narrow like that. So we would say no in terms of being precise. This one here, again, the results are centered on the true value, so it's accurate, but because they're also clustered much more closely around the true value, then we would also say that they are precise. This time though, we've still got a tight cluster of results, so they're still going to be precise, but this could be a situation where we've got zero error, where the instrument we're using is out of adjustment, and therefore the results are not going to be accurate. And finally, a big spread, so not precise, not centered on the true value, so not accurate as well. All right, now, when we talk about uncertainties or errors, there are two terms we use. One of them is called systematic, and the other one is called random. So talking about systematic, first of all, what I want you to do is I want you to look up your dictionary. Now, if you look up errors and so on, I think you'll find that in your dictionary it actually refers you to the term uncertainty as being the place. So if you look up systematic errors, that sort of thing, you'll actually find that where you've got to go and look for it is under the term uncertainty. And then you'll find that that also refers you to the terms precision and accuracy in the dictionary. Okay, so what I want you to do is write down a definition for what we mean by systematic error. And the good example that we've talked about already, something like zero error. Another one might be reaction time. When you start a watch, let's say, often I think there'd be a slight delay with the athletic sports coming up. When the starters start their watches, when they see the smoke go from the gun, there's always going to be a slight delay, and you'd always expect the time that they record, therefore, to be marginally shorter than what it should be. And so that would be an example of systematic error, or perhaps a faulty scale that doesn't start at zero. Can systematic error be reduced? Only by resetting the scale or adjusting the instrument, making some change to your experimental procedure that will allow you to reduce that systematic error. You certainly cannot reduce systematic error by repeating the experiment. As I said, the other type of error is known as random error or random uncertainty, And this, as the term suggests, is random. Sometimes you can get values that are larger than what they should be, that are larger than the true value, sometimes smaller than the true value. So they're scattered around the true value. Can random uncertainty or error be reduced? The answer is yes, it can. If you repeat an experiment and take an average of your results, it is possible to reduce the error. So effectively the pendulum experiment that you've already done, timing the oscillations of a pendulum, by timing 20 oscillations and doing it twice and taking the average, it actually reduces the random error. So sorts of things where this could occur: reading a scale, for example, just reading a meter rule. Sometimes you could read too big, sometimes too small. Even if the reading changes with time, so it could be something that's actually over a period of time changing, and therefore nothing to do with the instrument, but simply because the actual quantity is changing, that would introduce a random error. And reading a scale from a wrong position. I wonder if you can remember what that term is. If you read from a wrong position, parallax error, because it just depends what that position is as to what happens in terms of that uncertainty. In the third video, we're going to have a look at how we get into a bit more detail in terms of the analysis of these uncertainties.